All right, let's go through another example. If I take carbon dioxide, I'm going to count all the valence electrons available. Carbon has 4 electrons. Oxygen, each one has 6. Times 2 would give me 12 electrons. So I've got 16 electrons total. I got my total electrons down. Next, I want to draw the skeletal structure. Well, carbon's going to go in the center. Oxygens are going to go externally. Now I'm going to count 2 electrons in each bond and subtract from the total. So I've got 2 bonds here. That's 4 electrons. So 16 minus 4 leaves me with 12. Next, I'm going to complete the octets of the atoms attached to the central atom. So those 2 oxygens need to get the octet. Well, if I look at each oxygen, right now they are sharing 2 electrons. But I need to get them to 8 electrons. So each one of those oxygens is going to need 6 more electrons. Well, if I have 2 oxygen, each one needs 6 more electrons. That's 12 electrons total, which is going to leave me with 0 electrons left. And I represent those by adding those in as lone pairs. So I've got 3 lone pairs on each oxygen and a single bond. That's my 8 electrons. Okay, now you notice my total left is 0. I have no more electrons left. Okay, following these rules, get to this point first. We've got the oxygens, they're happy with the octet. They each have 8 electrons. All right, we place any remaining electrons in pairs on the central atom. Well, we have no electrons left, so none of them go on the central atom. All right, if the central atom does not have an octet, then we're going to form double or triple bonds. Well, if we look at that carbon, how many electrons does carbon have around it? Well, it has 4. So it doesn't have the octet. We now need to form double or triple bonds. Well, how do we do that? We don't have any more electrons left. We can't just draw lines. Those electrons have to come from somewhere. So what we're going to do is we're going to pull electrons from those external atoms. So let's say I take this lone pair off this one oxygen, put that in to form a new bond. Then that carbon would have 6 electrons around it. If I take a lone pair off the other oxygen and form another bond, then that carbon would have 8 electrons around it. Okay, so I move those in, and I get this. Now, each oxygen still technically has 8 electrons around it, and the carbon now has 8 electrons around it. Okay. Now, once I move those electrons in, though, I want to draw that solid line to represent the bond, so I end up with carbon double bonded to each oxygen. Okay, so everything is happy with the octet now. Now let's calculate formal charges and minimize those if possible. Well, remember, formal charges, that's the equation for it. So with carbon, got 4 valence electrons minus 4 bonds. Remember, simply because it's a double bond doesn't mean we count it once. Each one of those lines counts as 1. Okay, so 4 valence electrons minus 4 bonds minus 0 lone pair electrons gives us a 0 formal charge. Oxygen, 6 valence electrons minus 2 bonds minus 4 lone pair electrons gives us a 0 formal charge. So everything has a 0 formal charge, it's happy. So Lewis structure for CO2 would look like this. Let's look at another one here. Remember, we're going to follow these steps. Okay, so always follow those steps. So first, count all valence electrons available. I have a sulfur which has 6, oxygen which has 6, and I have 2 chlorines, each have 7, so that's 14 electrons from them, giving me a total of 26 electrons. So I'm going to keep my running total there. Next, I'm going to draw the skeletal structure. Usually we want the lower electronegativity atom in the center. Well, sulfur in this case is going to be the central atom. So with the skeletal structure here, sulfur is going to be the central atom. So sulfur is the central atom, oxygen, chlorine, chlorine are surrounding it, so I have 3 bonds around there. So now I count 2 electrons in each bond and subtract from the total. So I've got 3 bonds, which means I have 6 electrons, so 26 minus 6 leaves me with 20 left. Next, we're going to complete the octets on the attached atoms. So each one of those atoms has 2 electrons currently, which means they each need 6 more. That means 3 lone pairs on each of them. How many total electrons did I just use? I used 18, which means I have 2 electrons left. So I have 2 electrons left. That's going to be a lone pair. Subtract those 2 electrons out. I got 0 left. If used all my valence electrons. So now I check, does my central atom have the octet? It does. It has 8 electrons around it. Next, we want to calculate formal charges and minimize those if possible. So there's the formula. Let's look at sulfur. 6 valence electrons minus 3 bonds minus 2 lone pair electrons gives me a charge of +1. Okay, so I have a formal charge here of +1, and what I'm going to do to represent that, I'm just going to put a +1 next to the sulfur. Now, you don't always write out the formal charges in a Lewis structure. Usually you leave them off. I'm just doing this to show you where that charge is located at. If I look at my oxygen, 6 minus 1 minus 6, that's a -1, so that oxygen has a -1. And then each of my chlorines is 7 minus 1 minus 6. Chlorine formal charges are 0. Now, I want to try to minimize this formal charge if possible. Well, oxygen has a -1 charge, which means it has an extra electron. Sulfur has a +1 charge, which means it's deficient in electron as far as these formal charges go. So if I share electrons between the oxygen and the sulfur, I can form another bond between those two, and that's going to balance out that formal charge. So I get my double bond. When I calculate my formal charges again, you can see everything is now 0. I've minimized that formal charge. So my final structure for this should look like this. Now there's a problem though that we have. We have to be careful of when we're minimizing those formal charges or doing any of these Lewis structures. Sulfur is actually violating the octet rule. It actually has 10 electrons around it. Right? How can this happen? Well, this SOCl2 can exist like this. What happens though is that with sulfur can actually have something called an expanded octet, meaning it can take in more than 8 electrons. It can violate this octet rule. The reason why? Sulfur's in row 3. Well, if you start in the principal quantum number, the n equals 3, L can be 0, 1, or 2. So I can have 3s orbitals, 3p orbitals, and 3d orbitals. Well, sulfur has electrons in the 3s and the 3p. The 3d is completely empty. So those extra 2 electrons that are surrounding sulfur right now actually go into that d orbital because it's empty, so it can hold those extra electrons. If it was an element in row n equals 2 or n equals 1, we couldn't have this expanded octet. It can't happen because it doesn't have those extra d orbitals. Okay, so let's look at another example of this expanded octet. If I look at SF6, it's going to look like this. SF6, that sulfur has 12 electrons around it. Okay, it can have that expanded octet. Remember with these expanded octets, we can have these expanded octets if the central atom is in row 3 or higher. If it's in row 3 or higher, it has empty d orbitals that those extra electrons can go in. Now, to go along with these exceptions to the octet, we've also got something called an incomplete octet. With H2Be, the structure is just Be bonded to 2 hydrogens. That compound can be formed, but beryllium only has 4 electrons around it. Okay, that's why it's called an incomplete octet. It hasn't gotten up to 8. Mainly, I've run out of electrons. I can't get up to 8 electrons in this compound. There's no way I can do it. I don't have enough electrons, so the most I can have is 2 bonds. Okay, I could look at BCl3. With BCl3, I have plenty of electrons, but I'm not going to form double bonds with one of those chlorines. If I form double bonds with one of those chlorines, it throws my formal charges off. Right now, everything has a formal charge of 0, so it's happy. Now, with BCl3, it's stable, but a lot of times it can combine or coordinate with other compounds to make up that deficiency. So for example, if I put BCl3 and mix it with NH3, the electrons on that nitrogen, that lone pair on that nitrogen, can attach to the boron and form a bond between those. So then boron gets its octet that way. Okay, but those are 2 examples of incomplete octets, and those are the main 2 examples. We don't see the incomplete too often. Okay, so we have to worry about expanded octets, we have to worry about incomplete octets. All right, let's look at another example here. NO3 minus 1. The nitrate ion. Now I still have a nonmetal with a nonmetal. That makes this a covalent compound. Even though it's got a charge, it's going to have covalent bonds. All right, so we can draw its Lewis structure using these rules. So count all the valence electrons. Nitrogen has 5 electrons. We have 3 oxygens, so that's a total of 18 electrons from the oxygens. And then we have that -1 charge. Well, that -1 charge means we have 1 more electron. We have that extra electron. If it was a positive charge, we would have lost an electron from our total. Okay, so 5 plus the 18 plus 1 gives me 24 electrons. So my total electrons I start with are 24. Draw the skeletal structure. Nitrogen in the middle, single bonds to the 3 oxygens. 2 electrons per bond. We've got 3 bonds, so that's 6 electrons. I've got 18 electrons left. All right, I'm going to complete the octets. Each one of those oxygen needs another 6 electrons, which means 3 lone pairs on each, which means I'm going to use 18 electrons. So I've got a total of 0 electrons left. Any remaining electrons go on that nitrogen. Well, I have no remaining electrons, so I can't put any on the nitrogen. So I'm left with 0 overall. Central atom doesn't have the octet, so I need to form double or triple bonds. Well, if I form a double bond by moving one of those lone pairs in, I can get my octet on my nitrogen. Calculate the formal charges. Well, there's the equation. Formal charge of nitrogen, 5 minus 4 minus 0, so it's a +1. Now, to keep these other 3 oxygens straight, I'm just going to label them 1, 2, and 3. So oxygens 1 and 3, the ones that have the single bond, those are going to be 6 minus 1 minus 6, which would be -1 on each one of those. Oxygen number 2, which is the double bond one, that's 6 minus 2 minus 4, that's got a 0 formal charge. Now if you notice, when I add up all those formal charges, I've got 2 oxygens, each with a -1, plus the nitrogens +1. That gives me an overall charge of -1. Well, that's the overall charge of the nitrate. So something was going to end up with a formal charge no matter how much we wanted to reduce formal charges. Somehow we have to end up with a formal charge. Now, if I wanted to, I could try to reduce formal charges again by forming another double bond with one of those other oxygens, oxygen 1 or 3. But if I did that, then nitrogen would have an expanded octet. Well, nitrogen's in row 2 of the periodic table, so n equals 2. It only has s and p orbitals available to it. It doesn't have that d orbital, so it can't form an expanded octet. Nitrogen cannot form that expanded octet. So I'm stuck with this structure because I can't minimize formal charges anymore. Okay, so I take this as my structure. Now, since it's an ion, we need to do something else when we have an ion. And that is we're going to put brackets around it and put its charge outside those brackets. Okay, that's the appropriate Lewis structure for this NO3 minus 1. That would be our Lewis structure that we'd want to write out for this. Now, one problem we have though is, why did I use that top oxygen? Why did I use oxygen number 2? Aren't oxygen 1 and 3, couldn't I put the double bond between those? And if I put the double bond between oxygen 1 and nitrogen, it'd look like this. If I put the double bond between oxygen 3 and nitrogen, it'd look like this. Those are all equally valid structures. Because they're all equally valid structures, we're going to represent all of them, and we're going to write all of them out and put double-headed arrows between them, and this would be the appropriate way to write out the Lewis structure for this NO3 minus 1. These are going to be something called resonance structures. For the most part, they're exactly the same, except you can have that double bond move around to different locations. That's what a resonance structure is. We have movement of that double bond at each different oxygen. Okay, all of those are equally valid structures, and we're actually going to end up with an overall structure that's going to be kind of an average of those 3 structures. Okay, but main thing with Lewis structures, you need to represent resonance structures as well, and you need to write them all out. Okay, but that's going to be the end for covalent compounds and Lewis structures. Again, follow those steps I gave you. They're going to get you the right structure at the end. Don't skip around, don't try to jump around, don't try to go with something maybe you sometimes you learned it before where, certain things always get 4 bonds and you're always shooting for 4 bonds. Well, with the expanded octet, we now know that we can have more than just 4 bonds. Okay, so follow those steps that I gave you. It's going to be a better way to do this.